Howdy, I'm back again. So, this time I think what would be important to cover would be kind of the preliminary rule for thermodynamics, which is the zeroth law of thermodynamics. And it's called the zeroth law because it typically doesn't get listed with the other three laws, even though it's a pretty important rule. And I think there's a little bit of an irony to it, like, it doesn't get brought up, so then it gets brought up all the time. But besides the point, if it wasn't important, we wouldn't deal with this sort of principle. But essentially, from Fitzpatrick, which is this lovely textbook here, read it. We define a statement here, which goes as follows. If two systems are separately in thermal equilibrium with third system, then they must be in thermal equilibrium with one another. Okay, so how do we show this mathematically, basically, is the question that we're going to end up asking ourselves. So we know that if we have two systems which are previously in some sort of thermal isolation from one another, system A and A prime, each with respective energies E sub I and E prime sub I, we can bring these two previously thermally isolated systems into contact with one another. And if they're in thermal contact with one another, we know that they're going to trend towards some sort of thermal equilibrium. We say that the thermal equilibrium overall, we can just give it by the Boltzmann temperature beta, where the final temperature is defined as being a function of energy, and then the final temperature of A prime is also being defined as some sort of function of energy. So from here we kind of go back to first principles. So it follows from conservation of energy that if energy is conserved within our system, then our final energies, which are an average energy, instead of just a single variable here. I think you need to read back a little bit in chapter 4 in Fitzpatrick to get the full breadth of that, but for now, just stick with me with the average final temperature. That has to be equal to the initial temperatures of both of them. We know that our heat can be expressed as a difference of our final energy and our initial energy for both systems. So if we can make this particular substitution by moving our terms around, we'll find that the sums of our two heat equations for both systems A and A prime, Q and Q prime, will resolve to 0. Now, we must ask ourselves, why is that important? Why did we have to parameterize things in terms of heat? Well, doing so basically shows that the heat given off by one of our systems is equal to the heat absorbed by the other. That's basically all we're saying, right? And we've done that in examples beforehand. Whenever we're looking at something like a heat reservoir full of water, right? We'll have water in there and there'll be a heat reservoir. The heat that is exchanged between these two systems in trying to get to thermal equilibrium can be expressed as the heat gained by the water is equal to the heat lost by that particular reservoir, right? So, where do we move on from here? So if we have some system, our systems A and A prime, we bring them into thermal contact with one another, then they're going to exchange heat. We know that for a fact. We've established that with this particular statement. Now, they're only going to change into a new equilibrium state if the final state is more probable than the initial one. Or mathematically speaking, the probability of our final state having an energy corresponding to that energy state has to be greater than the energy level corresponding to the initial state. And then we're going to also apply the fact that if we take the natural logarithm of both sides, because natural logarithms are more slowly varying, and we like to abuse that principle here in statistical mechanics, then this statement also has to be true, where I've just done and said that the average final energy, or the probability of the average final energy, is going to be greater than the initial energy, and I've just denoted that as PF and PI. That's a me thing, that's not Fitzpatrick. So, once again, with this in mind, we can once again apply our conservation of energy rules, except now to our natural logarithm of our states, right? So the sum of our final energies of the natural logarithms of our state functions omega and omega prime have to be greater than their initial counterparts, right? That's the only way we're going to see some sort of evolution of our system. So we can set that up, and then we're going to use our handy-dandy Taylor expansion, which in Fitzpatrick in the edition that I have can be given by equation 5.3, which states that probability that a system A has an energy lying in a range E to E plus delta E is equal to some constant and then omega prime, where omega is equal to some function of E, and then omega prime is equal to omega of E. Is it plus delta E? No, it's the total energy minus our initial energy. That's the principle we use for that matter. So we applied that particular Taylor expansion to this system. And once we apply that Taylor expansion, it must follow that our temperatures, or our initial temperatures specifically, can be written as, we can express this as a difference between the two, where we have our initial temperature given by this natural logarithm, it's Taylor expansion, and then because this is a heat loss technically, omega prime represents that heat lost in Q prime, multiplied by some change in heat in the system as a whole, right? And then that's equal to 0, or greater than 0, which means Q has to be 0, or this has to be 0, but because we don't really care about the heat, we're more focused on the temperature itself, we can write that our initial temperature of our system A is greater than our initial temperature of our system A prime. And this has to be true for the identity that beta is equal to the natural logarithm of our state omega with respect to energy. And that's the identity that we're using there. So what does this necessarily tell us, right? Well, it tells us that if we have two systems that are separately within equilibrium with one another, they're going to have the same value of beta, then the systems themselves will remain in equilibrium when brought into thermal contact with one another. So if these two guys have the same beta and we bring them into thermal contact, they're going to stay at beta. And alternatively, if they have different values of beta, then the systems won't be in equilibrium when brought into thermal contact with one another. So instead, whichever system has a higher value of beta, or in other words, the one that has a lower temperature, because beta is equal to 1 over kT, right? So the smaller this is, the bigger this ratio gets. That system will continually absorb heat until we bring them into thermal equilibrium with one another. So, once we have acquired thermal equilibrium, we can throw in that elusive third system that has just been kind of hanging around in this problem statement this whole time, right? We have like, oh, a third system, right? So, if we know that A and B remain in thermal equilibrium when they're brought into contact with one another, and we introduce that third system, I'll call it A triple prime, or double prime here, then A prime and A double prime also have to maintain that same thermal equilibrium with one another, which by basically a transitive property, we state that, let me erase this, that if the temperature of ensemble A or system A is equal to the temperature in B, and B is that equal to C, then the temperature in A is equal to temperature in C, right? So we have TA if TA is equal to T B, and TB is equal to T, oh my goodness, TC, then TA has to be equal to TC whenever we have some systems in thermal equilibrium. That is what we mean when we have the zeroth law of thermodynamics. Things just find thermal equilibrium.